Okay, welcome everybody, and thank you for joining today. We are going to start the meeting. I'd like to introduce myself. This is a co-hosted webinar, an educational lunch and learn on the XJet technology. My name is Stephanie Gaffney. I'm the Vice President of Advanced Manufacturing here at the YBI. I'd also like to introduce Ron Furman. He is the Vice President of Customer Success. And Ron is a mechanical engineer with over 8 years of experience at XJet, and he specializes in managing customer service and overseeing the additive manufacturing center over in Israel. So next slide. I'd like to give a little bit of background of the relationship of both Youngstown Business Incubator and XJet. So XJet is an Israeli technology, and YBI is a traditional business incubator, and we help incubate companies that are within the United States, as well as companies looking to bring new and innovative technologies to the US. We saw great value in the technology, and we decided to acquire one of XJet's Carmel 1400 machines here in Youngstown. We are setting up a YBI AMC, which is an advanced manufacturing center, which would be a collaborative effort between XJet and YBI. The center here will be used as a demonstration and training and development manufacturing facility. So we'll be able to supply parts for customers, help them with R&D, help them with the design for additive, and then we will offer service bureau support. If you're interested in acquiring one of XJet systems or machines with their technology, either in ceramics or metal, we can definitely connect you back directly to XJet in Israel, but all parts would come here locally from the United States. So next slide. YBI has an advanced manufacturing center. We currently have 5 buildings on our campus, soon to be 6. The 6th building is going to be set up as a defense and innovation hub for aerospace, and it will be right here on YBI's campus. We'll add another 130,000 square feet. YBI specializes in all different programs. We have plastics, thermosets, metal castings, ceramics. We have a team of 6 engineers on site to help with that, and about 20 contractor employees that would help with many facets of your businesses. We support services like reverse engineering, 3D scanning, solid modeling, supply chain development, and commercializations of particular technologies, as well as writing SBIRs and STTRs for companies that are looking to get into do business with the defense and defense applications. We also have a lot of grant programs that will help support offsetting the costs of a lot of these processes for manufacturers. So if there's anything here that you are interested in learning more about, YBI can assist you with there and potentially have dollars to help offset the costs. So right now, I just want to go over a couple of housekeeping things. Everybody has control to turn their video and their microphones on and off. So just be cognizant of hitting keys and just being quiet during the presentation. If you have any questions for our presenter, Ron, there is a Q&A button on the bottom. Some of you may have to hit the more button with the 3 little dots for that to pop off, but we would like to have everyone put their Q&As right in there. We will bring those up at the end when we have a Q&A session, and we will be able to answer those questions right there. Or at the end, we will allow you to come off of mute and ask those questions directly to both either YBI or XJet. So I think that's it for me. So Ron, I'm going to let you go ahead and take it over from here.
Thank you very much, Stephanie. Hey, everybody. Let's go over and explain a bit who we are and what we are doing. So at XJet, we take pride in our groundbreaking nanoparticle jetting technology, which utilizes liquid dispersion of nanoparticles to revolutionize the additive manufacturing for metal and ceramics by eliminating the the challenges posed by loose powders, we ensure a safer, cleaner process while delivering unparalleled precision, design freedom, and quality. And at the end of the day, we can produce a very high quality and very complex parts for a small, medium, and large production size. Let's I'm going to show you the 1 minute of who we are and what we are doing, and then we will explain how we are doing it. Okay, so why we are unique? Our parts can end up with a very fine features. We can create almost any complicated geometries. Our surface is very good in quality. We are talking about N6 to N9, which end up with a very smooth surface. And we can create a very small inner cavities up to 200 microns. Our technology also enables us to create even pre-assembled parts because of our very small particle size. And our density is one of the highest in the industry. As you know, we are not using powder. We are talking about ink. This is our main advantages. We have actually nanoparticles in a liquid form, and we are direct jetting both model and support simultaneously. You can see an example here of the droplets with the small particles inside, and we are jetting both model and support together. It's important to mention that we are jetting only what we need. So you can see here that in this example, we are jetting the metal in this example, which is the black, and the support is the white. And we have almost no waste here. So we create only the desired geometry. This is how it looks like in a layer overview. We are jetting more or less 7 to 10 microns layer thickness. It depends on the material. And you can see how dense and how accurate it is compared to the competition. And also you can see here that we don't have any loose powder. So we have the support here, the white, that is going to dissolve during the support removal. We will explain what it means in a few slides. This gives us the very high resolution. The small particles together with the support material give us in the end of the day, to receive a very high resolution with a very high density, and enable us to create a very complicated parts. Let's explain what we are doing in 3 simple steps. So first step is we are direct jetting both model and support. Again, the ink is it's like any other ink. It's any other liquid. We have small particles inside. We are direct jetting both model and support on a hot surface. The liquids are evaporating, and then we stay only with the particles and the bonding agent. And jetting layer by layer, every layer is about 7 to 10 microns. And after the printing is done, we are taking the tray with both model and support, and we are taking the tray to the support removal station. It's a semi-automatical station. We are putting the tray inside, and the support is dissolved automatically. course, we need to take the parts out after the support removal is done. And then we are going to take the parts and put them in a furnace for sintering. This is our process, 3 steps, very simple and user-friendly, and no loose powder during this process. Our support, as I mentioned, is soluble in water. This is one of our biggest advantages because it's enabled us to create a very complicated geometries. We can create, you can see some example here. There are some parts with a very complicated internal cavities that it is either very expensive to create using different technologies or even impossible. And because of our support, we can create those complicated shapes. Few advantages that we can understand from our technology. One is we have one of the lowest, probably the lowest shrinkage factor in the industry. We're talking about more or less 15% shrinkage, and it's isotropic, X, Y, and Z. Different technologies, we are talking about 22 to 25 shrinkage, and it's very important when we are talking about the volume. It's almost the shrinkage compensation from different technologies is almost 2 times the shrinkage compensation, and we need to compensate almost 1.5 because we're talking about the volume, X, Y, and Z compensation. And our sintering temperature is very low because of our small particle size. We can sinter the parts a bit far from the melting point compared to the competition. This is one of the enablers for creating pre-assembled parts, and we don't need to put any coating between the parts to the other area of the part. Or if we need stages to support the parts, first of all, the part that actually needs stages is very minimal. I mean, we almost don't need to use stages, but in case we do need to use a stage to support the part during the sintering, we don't need to put a coating between the stage to the part because we are far for the melting point. Once the different technologies need to put a coating, like a ceramic coating, otherwise the part will be stick to the stage. Again, because of our process is very simple, we're talking about only 3 simple steps with almost no labor in those processes. The printing is very simple. I mean, we need to load between one printer to the other, few minutes. And then the support removal is also quite simple. We just need to put the tray, detach the parts, and that's it. Then we move the parts for the debinding and sintering in a single step. 3 simple steps compared to the competition, whoever know how difficult and long those processes are, and also the labor time and the time consuming. So it can be a very long process and very complicated. And some small parts can end up in our technology up to 48 hours. We are actually ready for the AI revolution that we know is going to happen. We're starting to receive a very complicated geometries that can no longer going to be manufactured using our current conventional manufacturing methods. So the only technology that can produce complicated geometries from AI generator parts are additive manufacturing. And we are doing it the best because our unique support. Again, our support is soluble in water. And you can see some examples of very complicated geometries here. And we don't have a free powder, which is very important. Whoever touch a SLM or the MLS part can understand how it feels when the part, when you end up with a powder on your end. You need to do many steps to eliminate this loose powder. And one of the most important things is we have a very minimal waste because we are jetting only on demand. Our process is very clean, safe, and automated. We don't have any loose powders. We don't have the lasers. We don't need to use spacesuits or filtration inside the system. We can open the system door. We can even put, we can get inside if we want. We don't want to, but we can get inside. There is no risk there. And our process is very automated. It's only 3 steps. Whoever knows how long it can take for every step in different technologies, it can take hours, and we will show an example during the in the file preparation. Our parts that we are producing, it's almost any shape. We don't have any. We have almost no waste here. You can see here some examples of the parts that we can create. We can create few parts in a tray. We can create many different parts in a tray. And we can create even very tiny parts that can end up with millions parts per year or 100,000 parts per year. Depends of the dimensions of the part. But we can end up with a very high quantity of parts per year. The average for our customers to actually earn profit is between a few parts to few thousands or 100 parts. That is not relevant for the MIM or the CNC. This is how it looks like. We have 2 systems, one ceramic and one metal. We have alumina and zirconia for the ceramic, and we have 316L and 17.4pH for the metal. For the post-process, we have a smart station, an SRT station, which is a simple table to support the customer to do the support removal. And we have our support that's built with a few UIs that enable us to produce the parts. This is how it looks like. We are planning the parts in the Autodesk NetFab. We are just organizing the parts. We can create either one part with multiple copies or many different parts. We don't need to design. We don't need to analyze or to do any other simulation. We just need to put the parts and select if we want a stage during the sintering or not. It's a very simple selective mode. And then we can control multiple jobs and systems, and we can of course start the job from the NetFab. Let's see a few examples and application that we can that gives us the biggest advantages. One of the interesting applications that we can do is surgical instruments for a surgical robotics tool. They need to change many surgical tools between one surgery to the other. They are actually using it almost for any single surgery. Our biggest advantages here is that we can create many different parts in a single run. They don't need to create a mold for million parts. They can create 5,000, 2,000, or 100 parts for a specific surgery type. From alumina, we can see many interesting applications of fluid control and filtration, because we can even put the alumina like as a sponge for filtration. We can filter. We can see some water filtration for the EV technology, or for just water filtration or the desalination. We also see some antennas and waveguide. From the metal and alumina, we can see some heat exchangers because of our support that is soluble in water. You can see the pattern of the inner shape inside the part, that we can create a very complicated internal shapes that can increase the utilization of the heat exchanger. And we are also can see a very customized part for fashion accessories, plated jewelry from even ceramic and metal. Let's see a few examples of parts together with the cost per part calculation to give you the idea of how much parts can cost. We can see an example of a very complicated geometry that if we will do this part, we'll manufacture this part using conventional technologies, it can cost a few $100s. You can see here an example. This is quite small part. We are talking about more or less 20 to 10 millimeter in size. In one platform, we can fit few hundred parts if we are organizing it well. In this example, we are talking about 152 parts per layer. We can see in this example 2 layers. In this example, we are seeing 150 parts per tray. This tray has 20 hours of printing time, and in this example, we can create 50,000 parts per year. The cost per part is actually imaginary. It's 6.5 per part, including everything. When we are talking about a system with 80% utilization, when we are talking about parts that up to 50,000 parts per year, it's or below, it's very increasing the revenue to produce the parts using additive manufacturing technologies. Here we can see the example of the surgical robotic forceps. We can see here again a part that is more or less 30 millimeter on 7 millimeter. We can fit 435 parts per tray with 15 hours of printing time. The total post-process, we are talking about 66 hours. In 66 hours, we can have more than 400 parts, and we are talking about 200,000 parts per year with an imaginary cost per part of $4. If a CNC will produce this part, it can cost like few hundreds. Here is another example of a very complicated part that is impossible to do this internal cavity with a CNC, different technologies, but here we can see another example of a very cheap part, $2 per part, and we can fit many parts per tray. In 5 hours printing time, we can receive more than 300 parts and almost 500,000 parts per year. Okay, a few takeaways to explain our advantages in summary. We have our support that enable us to create almost any geometry that we want, even with internal cavities. We need to understand that the manufacturing or the engineers are not quite into the additive manufacturing. They still need to change their mind in order to design the parts for additive. They need to use for a CNC or conventional technologies. But we know that in the future, once the engineers will change their mind, the state of mind, and will adapt it for the additive, they can earn a lot from this change. They can remove some material, eliminate the need for waste, and make the parts less heavy and more simple and cheap in the end of the day. We can create very fine feature, and the accuracy is very high. We're talking about plus minus 50 to 100 microns. And the surface finish is almost for most of the applications, we don't need to use any other technology to improve the surface roughness, although we can use tumblings to improve the surface roughness dramatically. We don't have any powder or slurry, and it's a very simple and user-friendly for the operator. And the end-to-end production is very good for medium and high quantity for productions. This is our sales team. We have Brad in North America, east side. We have Wang in the west side, and we have Ricardo in Europe. Thank you very much, guys. Stephanie?
Yep. So these are the YBI contacts that we have listed up here. So we have myself and Dylan, who is our advanced manufacturing applications engineer. Dylan will be able to review your parts for printability, design, get you some quotes, tell you about our programs that we have. And just one other thing that I wanted to bring up, YBI is on May 20th, 2025, hosting an Advanced Manufacturing Users Expo. It will be from 11 a.m. to about 5:30 p.m. And we will be talking about all different applications of additive engineering. So this technology will be featured, as well as metals printing, polymers printing, binder jetting, all at that conference. We are expecting about 200 to 250 actual users of the technology, so manufacturers that will be at that conference. So next slide, is there anything else that you want to show? But we do have some Q&As in the chat here. There's 5 of them. So we can go over some of the questions here. The first one that we have is, how difficult is the sintering furnace to implement? Facility infrastructure, setup and training, and ongoing operation. So Dylan, if you would like to answer that question and talk a little bit about the furnace that we have and what it took to install that, and the type and the temperatures that that furnace needs to achieve to sinter the parts properly. I will go ahead and let you take that one.
No problem. So our furnace here, it was around $30,000. Pretty actually cheap for furnaces of this category, but it's an open air furnace, so that doesn't need any inert gases or anything to get to center these parts. In particular, I believe for the metal systems, you would need a furnace with inert gases, so you would have to implement. But for ceramics, you do not. Infrastructure wise, I believe it was around 5,000 to 8,000 for just electricity hookup and anything, and to dissipate the fumes and such in a correct way. Ongoing operation, it's pretty much plug and play with the furnace after you get it set up. It's not too hard to keep it clean and keep it going as maintenance wise. You just have to make sure everything's working correctly. Make sure any of the heat elements aren't broken, things like that. And then just keep on centering from there. I think that should pretty much cover it. Training setup wise, it's pretty much all manual based. They didn't have anybody come out to teach or train us as well.
Thank you, Dylan. Joel, I don't know if that answers your question, but feel free to come off of mute if you have any other comments about that. We do have another question from Joel, and I'll send this one over to Ron. How much experimentation is needed with print and center parameters for a part to achieve the published material properties?
Okay. So first of all, our shrinkage is pretty much stable, so we don't need to change it. We're ending up production with a plus minus 50 or up to plus minus 100 accuracy with no need to change, and we don't need any too much experiments. So we just, as I mentioned in the NetFab, we just need to put the parts. The shrinkage, by the way, is done automatically. We need to select the recipe. The recipe is can be generally either model as a support, we called it, that we can support the part during the sintering, or pure support, as we called it, that we don't need to support the part during the sintering. So it's a simple selection. We just need to select the part. It's a training that every customer receiving during the installation. It takes a few days for us to train the customers to do it. May I answer your question here?
I can add something. It's Guy. The material, the sintering profile is set. We deliver the solution with the recommended sintering profiles. You typically do maybe 1 or 2 runs just to verify that it works the same on your facility, and from that point on, it's just monitoring. It's not supposed to change. You're supposed to get the density and material properties the same time every print. Right, Ron? I think that was the question.
Yes.
Part of the question. Yeah.
Thank you guys. Yeah, if I could clarify one thing. So if the published material density on steel parts is 97 to 98%, does that translate to 97 to 98% of properties such as strength or other properties that you would get from a wrought process, or is there other data on what the parts can actually achieve on strength primarily?
Yeah, it's a good question. Generally, the density is 97, 98 for the metals. For the ceramics, we're talking about 99 point something, okay? 99.4, 99.6, depends on the material. But once we are talking about the density, the other mechanical properties are same or better than the conventional manufacturing methods. For the metals, we are mainly compare ourselves to MIM. So we are either similar to MIM or better in terms of mechanical properties.
Yeah, but just to be cautious, on ceramics, the sensitivity to sintering is very low. In metal, it's not the same. So your final material properties may vary. Depends on, not a lot, but may vary, depends on your sintering furnace, environment, whether or not you do heat treatment afterwards. So in metal, it's not straightforward. It requires understanding on the, or let's say, clear understanding of the final properties you're looking for and verification that the sintering profile and environment. For example, if you sinter in a vacuum or you sinter in gas environment, if you do heat treatment, this can change the final material properties in metals. So we give like the standard profile, which is out of the process, but then some customers, they have special treatments in order to increase the performance.
Okay, thank you guys. That pretty much captures my whole question. It seems like there is some variability based on different factors, but they can be managed if we understand the targets and the expectations. So I appreciate that.
Yeah, exactly.
think you're on mute, Stephanie.
I said, while you're here, you have one other question in the chat. If you want to go ahead and ask that directly. It was about the lattice, I believe.
Oh, yes. Thank you.
Yes.
I was curious if the software can automatically core out part designs or add interior lattice or other things like that to make a print go quicker.
Yeah, we are using the Autodesk NetFab. In the Autodesk NetFab, there are some features for lattice creation. Of course, it's a paid version, so they have a few options for lattice structures. But so the answer is yes, you can adapt it.
Great, thank you.
Next question we have here is what temperatures can the ceramic materials withstand in the end application?
It depends on the environment, of course, and the application, but generally, zirconia and alumina, more or less, in their application desired need temperature. I don't remember exactly, but the application temperature is same as conventional temperature.
It's very high. It's more than 2000 Celsius, but we are not expert, we know that some applications involve pouring a melted metal through a ceramic filter. We are printing our own plates for our metal sintering, so we know it withstands 1300 degrees Celsius. So it's the typical natural qualities of the ceramics. It's not special.
This is Lou Mazzoli. I asked that question. The reason I asked it was for the parts to be used in furnace type applications, as far as components of burners that are reaching temperatures like heat treat furnaces up to possibly 2,800 degrees.
2,800 degrees starts
Fahrenheit.
to be Fahrenheit. So I don't know.
Yeah.
Sorry, what is it in Celsius? Sorry.
The zirconia, the melting point for the zirconia is close to 1450 or 1500. As Guy mentioned, we are using zirconia and alumina plates for our metal sintering. And the metal sintering, we are talking about something like 1300, and we are using those applications all the time. Once we try to go for the 1500, we see that the zirconia is still there, but again, the zirconia is, for the application for the zirconia, is lower than the melting point, lower than the 1500 degrees Celsius. Alumina is a bit higher than this, but again, it depends on the application, depends on the environment, depends on the application.
Yeah, I see here. I think 2500 Fahrenheit is well in the spec of the material, but this is not XJet. This is nature. This is the ceramic application expertise. So it needs to be similar like any other way you make it.
Okay, thank you.
We have another question up here from Clement. In the presentation, you showed a picture of a heat exchanger. Can you give an example of the types of fluids and what temperatures that were running through those heat exchangers, or some case studies or examples of what types of materials would run through those? Okay,
those that we shared are like in marketing. We have some parts that we cannot share, that we know our customers using them as an heat exchangers, mainly for gases to cool some parts. The temperature that they are using are lower than 0 degrees Celsius in some cases. Again, they're using nitrogen or different gases for cooling applications, mainly gases for cooling. Of course, there are some other fluids that they can use, but the biggest advantages in the very, very complicated shapes are from gas.
Clement, do you want to come off of mute? Does that fully answer your question? Do you have anything else that you want to ask directly?
Yes, it does answer. Thank you very much. I'm concerned about brittleness at the below zero temperature. Is that an issue, or has it been?
No, not again. It depends on the material. Our material, I don't have any concerns in terms of the below the zero.
And these are in alumina.
No, we're talking about the metal. In
Okay.
my example, was made for the metal. For the alumina, I don't know for sure the actual temperatures. In many cases, the customer is doing their magics and they are not sharing with us all the time. In some cases, we do know what they are doing.
Okay, thank you.
Sure.
Okay. Next question we have up here is from Keaton. Does the MPJ technology reduce the needs for setters during sintering with the reduced shrinkage?
Yes, it is, definitely. We see that, for example, in the binder jetting, almost any part that has a bit increase in the angles need to use a setter. And in our technology, most of the parts that have a very small angle don't need on the geometry. Of course, there are some geometries that you do need. This, again, the expertise that you get during the installation and the training. But for the answer is yes. The shrinkage, the lower shrinkage, and the far from the melting point sintering temperature, it is reducing the need for setters.
Okay, Keaton, any other questions you have about that? If you want to come off and mute and ask any direct questions.
No, that was it. Thank you.
Okay. We have another question in here. Have any of your customers, either in Israel or in the States, achieved medical device marketing clearance, full compliance for XJet printed zirconia for medical implant applications? Do you know if any customers have?
No, that I am familiar with.
No, only in China.
I know YBI was working with a company that we were producing medical shielding parts with, that we aren't able to show the design, but I know they were doing testing on some animals in that space. I don't know if they've gotten past that stage. That's our one experience that we have with medical and where we are with that process. So
yeah. No implants. If you're talking about body implants and not dental implants, that's a long trip. And no, I don't know of anyone who has actually done that without technology.
We have one other question in here about the size of the bill plate and about upgrading the size of that from the current size to a larger size, and what you think you'll be able to achieve.
Yeah, the Camel 1400 is not supporting 280 millimeter, but we do have a new product, Camel 5000X, that is with our new technology that can produce 280 on 500. So it's a double platform, and It's the new platform. It's not the Camel 1400.
I think that's all the questions we have right now in either the chat or the Q&A. We welcome anybody that is on the call to, if you have a question you want to ask anyone directly, you are more than welcome to come off mute and ask those questions at this time.
The bill of items highlighted a couple of small parts that could be printed at hundreds of thousands to millions per year. Would those be printed at the full Z height on the tray, like you're printing multiple layers of parts, or is it more recommended to only maximize the area of the tray and not build up?
Okay, we do, as I shared in the example, we do able to produce a stacking mode that we can put one part on the other using our support material. We can do the stacking option up to certain height. We're talking about 30 to 50 millimeter Z dimension height, that we can either print one part standing up to this dimension or stacking option.
And Dylan, can you give a little bit of insight and what's the maximum that we've printed to for the Z height on our machine here locally?
Ceramics, alumina, we've produced parts up to 75 millimeters height.
Okay, great.
We believe we can go higher, just we haven't tried, mostly because of how long the prints are when you are reaching those heights.
Yeah, it's a good question. By the way, two points here, because it's a bit different from other technologies. We print the parts horizontally. Okay, that's the way the technology works. So most of the parts, you know, they're not cube. So that's why the Z height is not such a big constraint. So we can print 25 centimeter parts that are 5 centimeter high. Now, because the setup of the system is really short, there's no powder clearance, depowdering, repowder, etc. You just need to, 20 minutes, half an hour, and you can get to the next job. There isn't much value in printing a lot of layers of parts. So most of our customers don't really do that. You print tray by tray, and that's it. It doesn't really hurt your productivity.
So when you're putting parts on the plate in general, you're trying to usually set it in an orientation where your Z height is minimized to its max. That way you have the shortest print time possible. Yes, it's not only because of the shortage print time, it gives you the best quality of printing. It's counterintuitive. I know that in other technologies you typically want to put the parts standing up, but in our technology, the quality is better when they are horizontal, even in complex geometries. And then yeah.
Go ahead if you had anything else you want to add there.
Yeah, and then the whole handling is easier. First of all, the printing is faster. Then putting it in washing is easier, and then it's just, this is the way it works best. The new platform 5000X is not only having a double tray, it also will have a double speed on the Z height. So it will be 4 times more productive than the current one. And it will use a recirculation printer technology. So the maintenance time and the waste are lower. The waste is very low as it is now, but it's going to be even lower. So that's how we go to a high throughput. So tray size and Z speed. This is the way to achieve throughput.
Okay, we have another question here. What about the file preparation software? How do the models need to come in? What is the preferred method? And what would be the cost of the software if a customer needed to acquire that?
Yeah, the software is purchased through Autodesk. We're talking about NetFab. I think it's an yearly subscription of $4,000 to $5,000. And the file preparation is quite simple. We just need to orient the part and duplicate it if we want few of it, and select the recipe. As I mentioned, whether we need a setter for the sintering or not. This is more or less the steps that need to do during the tray design. And then we press build. We don't need to simulate. We don't have any simulation. We don't need to do support generation. Everything is done automatically.
And for the customer sending files in that you're looking to have evaluated for the technology and printability, we would require a 3D model of the part or parts. We can build, multiple different parts on a build tray. So if you were looking to prototype 7 or 8 different parts, we can do that all in one print, which would need to come in the form of a STL or a step file, a 3D model. Can you go over a little bit of information on the support materials for the process for both ceramic and metal and how that works?
Yeah, of course, the support, I cannot explain what is the material of the support because this is our IP. But it's so simple that we just need to put the tray inside the water, and then it dissolves automatically using a filter. So we put the tray with the parts after the printing is done. Immediately the support starts to dissolve, even because of the water. The water, as we know, can penetrate for the most difficult cavities. So the water penetrates and dissolves the water from one of the most difficult geometries that we even cannot imagine that it can dissolve from those geometries. You're on mute, Stephanie?
Yes, I am. So that brings us to 5 minutes to the top of the hour. I don't see any other questions that we have in the chat or the Q&A. So I thank everyone for attending and spending your hour-long break with us. And if there are any questions, follow-up questions, we will be sending out a version of the PowerPoint to everyone that registered for the event. It will be a shareable version, and all of the contact information that you will need to reach out to us will be included in that presentation. So thank you very much. And Ron or Guy, do you have any final comments?
Yeah, I would like to thank you from, professionally and personally on attending. We are very proud that you joined us. We are will be very happy and welcoming any requests for benchmarks or other questions or inquiries. And we hope that soon we can also do metal, the same like we do ceramics. YBI is a really fine partner, and both of us together can give you the full package. YBI with the US presence and expertise, and we as a technology provider. So thank you. That's all I can say.
Thank you. And one of the other things that we forgot to mention, YBI is ITAR compliant and is able to do all DoD contracts and government work. So if that's a concern for anybody, we are able to handle that as well. So.
If anyone is interested in coming out to the facility and seeing the machines and seeing how we have everything set up, we're more than happy to accommodate. Just go ahead and reach out to me or Stephanie, and we can work on getting that set up.
Right. Thank you everyone for attending and have a great afternoon.
Thank you.
Bye-bye.